Hello everyone, I'm Xinghua, coming from Institute of Animal Science and Veterinary Medicine, Shandong Academy of Agricultural Sciences. It's my great honor and thanks very much for Science for giving me this opportunity here to share my report of sorption and desorption behavior and mechanism of oxidation recycling on soil aggregated organic matter, separated from soil and sediments in the Yellow River Delta. Since penicillin was discovered in 1928, antibiotics were widely used in healthcare and cultivation. China leads the world in volume of antibiotic production and usage. From this graph, coming from a research article of EST, we could know that the total antibiotic usage in China was about 16,000 tons in 2013, for the selected 13 target antibiotics, veterinary antibiotics accounted for 84%. Antibiotics are poorly absorbed in the gut of animals, and as much as 14 to 17% of each dose is excreted into the environment. Potential environmental risks posed by antibiotics have lead effect on ecosystem and health. Soil is the final determination of antibiotic when they enter the environment. Soil formation and contamination are mineral freeze, soil organic matter, soil pore, and soil organism activities. The behavior of them in the soils are subject to mineral freeze complex of SOM, occluded by the soil pore and degradation of metabolism. The most study focused on sorption onto mineral freeze studies such as surface sorption sites, metal iron complex, iron oxide surface sorption, and sorption to some dissolved organic matter and humic acid. Association of antibiotic to DOM is much stronger than participated from hydrophobic interactions, possibly due to the different association mechanism. The effect of humic acid on the sorption of antibiotics showed that the contribution of the coated HA to OFL and ORO sorption in the complex was over 28% of the total sorption. The effect of black carbon also has strong sorption ability to antibiotic, and the surface absorption mechanism was the macropore filling effect and the size exclusion effect. The QC values of HOC were negatively with the relative alkyl carbon content. Soil aggregated organic matter composed of free particulated organic matter, intra-aggregated particulated organic matter, and mineral-associated organic matter. FPM accumulated on the surface of soil aggregate and have relatively higher turnover rate, and thus it is part of the soil organic carbon pore. FPM, which is found within the aggregates, is part of the intermediate active carbon pore because of its aggregate protection. Mineral soil organic matter is stabilized by its small size and is protected by minerals from biochemical resistance decomposition, and thus it has been equated to the slow organic carbon pore. Soil aggregated organic matter separated from wetland, farmland, and oil wasteland, and the separating method was shown as the following diagram. That is, each air-dried soil sample will pass through a set of sieves containing 2,000 micrometer and 263 nylon septum, partially within the potential water to obtain soil aggregate organic matter. As I use the AI with the density was of 1.65 gram per centimeter, and then the IPM, and IPM in the fraction was further used in the sorption and desorption experiment. The microstructure of SOM in different humidification. This is under the macroscopic images. This is the SEM images. From this image, we could know that the SOAM was mineral and organic complex. Thus, to further qualify and characterize the sorption and desorption behavior of OTC on the organic components of coastal SAOM in different land use types in the Yellow River Delta, we determined the dominant sorption and desorption mechanisms of FPUM, IPUM, and SOM. They were used HF treated to eliminate mineral influence, which did not significantly alter their chemical structure. This is the abundant chemical function groups of SAOM. Main chemical functional groups of SAOM from wetland, farmland were aliphatic carbon and hydrophobic carbon. Dominant groups of SAOM from the oil wasteland sediment were aromatic carbon. This is a relative optimization of organic carbon in different regions. This is the opportunity of SOM containing physical and chemical dispersion properties. The sorption kinetics shows that OTC sorption kinetics on SOM can be divided into a rapid process and an equilibrium process according to the sorption rate. The rapid process continued for the first 3 hours and was followed by a sorption rate reducing until it reached a state of equilibrium at 24 hours. This was due to SOM surface providing a surface driving force to counter the resistance mass transfer OTC to the SOM surface sorption site in the first 3 hours. The SOM surface sorption site gradually reduced with the driving force weakening, and the resistance function decreased the SOM sorption rate until it reached the state of equilibrium. The sorption mechanism of FPUM O, W, and F was somewhat different from the other 6 IPUM and MM because a linear-like sorption process appeared between the rapid process and the equilibrium process. It was advantageous to conduct the sorption experiments to control the migration rate of the whole OTC under the influence of the actual aquatic environment. The sorption desorption of OTC was inversed. The desorption inverse process of sorption and consists of a rapid desorption process and an equilibrium process. We used 3 models to fit kinetic data, and the results showed in the shows that the intraparticle diffusion model was better aligned with the actual kinetic process. This is the sorption rhythm. We did not find any obvious natural decomposition under the experiment condition because condition increased with increasing concentration of OTCs of solved solution. The fitting result also used a linear equation, like mirror equation and Frondeli-C model to fit the date, and QC also showed in this table. The KD values from linear equation ranged from 28 to 167, and the alpha values ranged from 0.8 to 0.98 for the non-SOM. The KD values of FPMW and FPM off obtained in this study decreased tenfold compared with those of FPM raw and FPM F raw, whereas the FPMO increased slightly compared to the FPMO raw in our previous study. This result indicated that the demineralization treated to remove SAON minerals could decrease the sorption affinity for OTC. The desorption rhythm indicated that some OTCs still reside in SOM, and we fitted the date also used 3 models. All of the fitted results were satisfactory, and desorption contained KD. KDS indicated the extent of OTC desorption from SAOM. The desorption proportion of FPM was no more than 21%, and that of the IPM was no more than 25.9%, whereas the desorption proportion of MSOMW was 33.6%, which was the highest of the 9 SOM. This was due to the fact that MSOMW had a relatively lower QC of MOMW and a high SSA and mesoporous surface area. The PCA result indicated that organic carbon function groups, such TOC and black carbon of SAOM, directly affected the sorption and desorption affinity between OTC and SAOM, although the physical surface and chemical organic carbon characteristics have significantly different impact on OTC sorption and desorption. The HI at 7 different OTC initial equilibrium sorption concentration levels. Sorption and desorption hysteresis were affected by physical surface characteristics, whereas OTC initial equilibration sorption concentration was lower than 200 microgram per liter. Sorption and desorption hysteresis were likely to be affected by chemical organic carbon composition. We interpreted this finding to mean that it was due to the strong bonding induced by the animal group of OTC and the carboxyl group of SAOM at initial OTC equilibrium sorption concentration lower than 200. Previous studies have shown that FTIR spectra can be used to correctly writes the changes in the functional groups, a chemical bond between the absorbent and adsorbated. Thus, gives SAOM had abundant chemical organism function groups. We further studied OTC sorption mechanism that was affected to gain supporting evidence for the dominant mechanism in SAOM and OTC interaction. The results indicated that the nature of adsorptive interaction between them, despite the fact only few absorbed OTC molecular leveled off from the strong background signal of SOM. The spectrum before and after OTC sorption shows that the intensity of a significant number of changes in the structural functional groups shown, and the FTI spectra showed the sorption mechanism included hydrogen bond, electrostatic interaction, and pair interactions. The conclusion is that SOM had great OTC sorption capacity, ranging from approximately to 3,000 microgram and kilogram per kilogram, and the desorption property was no more than 33.6%. A slow organic carbon pore had greater OTC accumulate capacity than the intermediate active pore and the active pore, while OTC was more likely to reside in the active pore in wetland and oil wasteland than the organic carbon pore in the farmland with human activity interference. The HI was the hysteresis was affected by SAOM's physical surface characteristics when the OTC initial equilibrium sorption concentration was higher than 200. When it was lower than that, it was affected by organic carbon composition. Hydrogen bonds the fourth conclusion is hydrogen bonds, electron interactions, and pair interaction dominated the SOM and OTC interactions. Acknowledgement. The authors are grateful for the financial support from the National Nature Science Foundation of China and the Innovation Ability Improvement Project of Shandong Province and Technology SMEs, and the Innovation Project of Shandong Academy of Agricultural Sciences. Okay, this is my report. Thank you for your attention.